Hi, this is Professor Fernandez, and this is video 2 in lesson 13. So we're continuing our work into linearization in this video. In the previous video 13.1, we talked about linearization and kind of its origins, and I'll just do a very quick little review verbally there. The idea was that we had a function and we had a point x equals a, and then we wanted to draw the tangent line to the function at that point. And then we saw very clearly that as I zoom in to x equals a, the function and its tangent line start looking very, very much like each other, right? So this is zooming in and then zooming in more, right? Clearly it doesn't look as clean in the picture I've just drawn, but the notion that is there. And so linearization as a concept is really tied up with the idea of approximating a function using its tangent line. So that's what we're going to do now, right? We're going to talk about linear approximation using this example from Calculus Simplified. So down here, I put again the definition of linearization. So I'm just going to zoom in really quickly. I talked in the previous video, video 13.1, about how linearization and linear approximation are two slightly different concepts. So what we're reviewing and working on in this video is linear approximation, the first part of this definition, right? So what is linear approximation? It's when you write out the equation of the tangent line near whatever a value you are given. That equation in the tangent line is called the linearization of f at that point. And then using that equation in the tangent line, you approximate the values of f of x, approximate, using the values of that tangent line. So in other words, values of f of x are approximately the values on the tangent line, L of x, for x near a. Doing this, working with this, calculating this is called linear approximation. Okay, so let's go back to the example that we're going to solve in this video. So let's see what it says. Suppose f of x is square root of x. Calculate the linear approximation at a equals 1, and then use it to compare your estimate of square root of 1.05 to the actual value. So we actually did a lot of the work here in the previous video. So I'm just going to recall what happened there. Recall from video 13.1 that we had calculated the linearization of square root of x at the a equals 1 value to be L of x is 1/2 times x plus 1. F of x is approximately its tangent line for x near a, which is the linearization idea, becomes, in this case, f of x is square root of x. Square root of x is approximately the tangent line, which is x plus 1, for x near a. In this case, a is 1, for x near a equals 1. So this is the answer to part A. Okay, we have expressed square root of x as an approximation of a linear function, which is a tangent line, near a specific x value, x equals 1. Now what I want to do, so let's go back to part B and let's talk about that approximation. We also did this at the end of the previous video, so I am going to pull forward some of that information, but let's look at it. So part B, use your linear approximation from A, in other words, use this red box, to estimate square root of 1.05, and then compare your actual estimate to the value of square root of 1.05. So what would I do here? First of all, just a tiny point, right? So f of x is square root of x. Square root of 1.05, this is therefore f of 1.05. Okay, so this is something, what I'm about to do is something I did not do in the video before. So I'm going to say f of 1.05 is approximately, and I'm going to go back to let me use a different color. I'm going to go back to this, right? So I'm going to put in 1.05 here for x, 1.05 here for x, 1.05 for x, and then use the a value, which is 1 that I'm given, just to show you a slightly different and useful way to view this. So f of 1.05 is approximately L of 1.05 for 1.05 near 1. All right, and you might be looking at this and saying, why? This is so weird. This is so strange. Well, this is me hopefully helping you to take a concept that we talked a lot about over this video and the previous video, and then see how things relate to each other, right? So this approximation here literally says the value of the function at x equals 1.05 is approximately the value of the tangent line at x equals 1.05. And then we don't really need this part, but it is a qualifier, right? It reminds us that, whatever x value I'm going to substitute here into this approximation, it really should be near the a value of the problem. For example, if I asked you to redo this problem and approximate square root of 97 using this approximation, well, then you would say f of 97 is approximately L of 97 for 97 near near 1, which is the a value that we are using in the problem. And that is really not going to work out so well, right? Or I should say, there's no reason you would expect that to work out that well, because 97 is not near 1, right? 97 is pretty far away from 1. However, 1.05 is near 1. So again, the whole point of showing you all this is to show you how these little pieces fit together, right? We now can then unpack what each side of this approximation is. F of 1.05, like we set up here, is square root of 1.05. Great. Approximately L of 1.05, well, L of x is this. So I'm just going to substitute in 1.05 into this function. And then, I don't need to keep writing for x near a because 1.05 we already know is near 1. So I'm going to just then work out what this is over here. And we did this in the previous video as well. So I'll just go a little fast here. 2.05 divided by 2, right? So that gives us 1.025. So our approximation for square root of 1.05, I should put a little approximation here, is 1.025. What is the actual value of square root of 1.05? It is actually 1.0247 ... So you can see that we got the 1 right, we got the 0 right, we got the 2 right? And then the approximation that we came up with starts differing at the 3rd decimal place, right? From the 5 and the 4. But in some sense, it's just a rounding, right, of the actual value. So this is really, really impressive for a technology, quote unquote, that does not use calculators, does not use a computer. And as I said in the previous video, this was one of the many, many ways in which, when calculus was developed, people noticed that this was a very useful set of results and a very useful way to approach problems that at the time were really problems. How do you approximate a function? Again, having no calculators or computers. Okay, so I'm just going to zoom back a little bit and say a few things. Most important thing for this video is that, unlike what we did in the previous video, 13.1, this was about calculating the linear approximation. So again, linear approximation involves approximation. So you can see approximation happening everywhere on this video, right? And the linear approximation really is the idea that the values of the function can be approximated by the values of the tangent line, so long as the x values are near that point of tangency A. This is all distinct in a subtle way from linearization, right? So linearization is down here. And linearization, the linearization of a function at x equals a is just the equation of its tangent line. So the concepts are related. I'll refer you again back to video 13.1 for a detailed discussion of how they're related, but just wanted to end with that. If you're asked for the linear approximation, you're being asked for something like this, right? Give me an approximate equation that relates the function to a line, notably its tangent line. If you're asked for the linearization, you're really just being asked for the equation of the tangent line at that a value. Thanks for watching.